So here's the next little thing we're going to consider, and we've talked about variance, and now we're going to learn about something called standard deviation. Standard deviation is a super important concept, so I'm going to choose insert row below. I'm going to put in here standard deviation. Standard deviation is a super important concept in statistics. We're going to be working with standard deviation throughout the rest of this semester. And what's like a standard deviation? Like, what's the standard deviation? You know, just like think about that phrase, standard deviation. Like, what is like the normal? Standard could be kind of normal. Hey, this is our standard. This is the way we normally do things. This is like the standard, right? How we want to do things. So standard could be normal, it could be some way that things are normally done. And standard deviation is the amount that, you know, is a deviation from the mean. It's a measure of a deviation from the mean for a data set. So it's a measure of a deviation, and so a deviation is a numeric calculation. It's a descriptive statistics that we came up with through a mathematical formula, which was logical, right? And it's a measure of a standard deviation from the mean, and that's going to be different for every data set. Well, the reason people came up with standard deviation, statisticians came up with standard deviation, is because variance is not at the same scale as your data. So to calculate the variance, we squared the difference between the data point and the mean. 8 minus 10 is -2. We then squared that. We squared that. We squared it. And once it was squared, we got 16. And then once we had 16, we came down here and we divided that 16 by how many pieces of data there were, -1. Why -1? Well, at a technical level, I don't know. But just the theory of it, because that's like getting a PhD in statistics, but the theory of it is that that somehow puts it all in relationship to the data in a better way, as opposed to just dividing by your data. That more closely approximates what's truly going on with the population when you divide by n-1. And that's why in this formula here, for a sample, you divide by n-1, but for a population, you divide by n, all of the elements in the population. But mathematically, for some reason, people who get PhDs in statistics, they have figured out that for a sample, you need to divide by n-1. And that helps you more closely approximate what's going on with the population. And there's many points in your life where you just say, oh, okay. And you just say, that person knows a whole lot more about air conditioners than me. I'm going to let them handle it. And that's what's going on here, right? So for a sample, you divide by n-1 because that helps you more closely approximate the population. And that's exactly what the textbook's going to tell you. So here we have, we have all of our data, the difference between the data point and the mean. We got -2, and then we squared it, and then we divided by a number. And for a sample, it's n-1, and for a population, it's n. But what's going on here is we're dealing with a number that came from squaring the difference between the data point and the mean. We squared it. We squared it. So we're like at a double of what that really was. We're at a double of what that was, right? When we created variance, it was this difference times itself, or squared, and then added up, and then divided. And so that kind of like made the number larger. And so for standard deviation, this is all you do. The square root of this variance, right? Let's just bring it back to not being squared. Let's bring it back to this not being squared. The square root of the variance, so we take the square root of 4 and we get 2. And look at what just happened there, right? Because when we look up here, what is the standard deviation around our mean of this data? If we had to choose a number, I'd say it's 2, right? Like that's the standard deviation. It's either going to be 10 or it's going to vary by 2. It's going to be 8 or it's going to be 12. Wow, standard deviation is 2. So that's kind of interesting, right? Hopefully that was kind of like, oh, wow, that's kind of cool. It is kind of cool. And if we come over here and we do the square root of this one, right, it's not going to be as like obvious, but the standard deviation of this one is going to be 11.597 something. And so when you look at like how much do things vary, how much does each data point vary around the mean, the standard deviation of those data points around the mean is 11.597. But I think this example is way more clear what standard deviation does, because you can really see here that these data points, the standard deviation they have around the mean is 2. All these data points, the standard deviation they have around the mean is 11.597. Now when you compare these two here, it kind of is like an easier comparison. Like these numbers seem to be more on the scale with these numbers, and this number here seems to be more on the scale with those numbers, as opposed to 134.5. So I could really see why standard deviation came into existence, and I could also really see why it's super useful as a numeric scale. And in our little example here, it makes complete sense. But what if we had like some figures that were like, you know, wasn't Robert's Parts Company, but we had something like over here. I'm just going to do one with some really different figures. I'm going to paste all that. I'm going to put Elon's Rocket Supply Company. Okay, Elon's Rocket Supply Company. So every time you want a rocket, you could order something from Elon's Rocket Supply Company. And then this first number here is going to be like how many days did it take? And we're going to do, it took, you know, like 5 years to get a rocket. And then, you know, they actually had one in stock. Well, and then we'll do this one, took 4,500 years. I don't know how many, 1,500 days, right? 1,500 days would be 5 years. Less than 5 years, but close. And then this one we'll do 7,200 days. And then this, no, that's too many. We'll do like 1,750 days. And then we'll do here 1,435 days. And then we'll do here, I don't know, like 1,675. And then we'll do here, I don't know, what do you want to do there? We'll do 1892. All right, good enough. And now I want to copy all this here, so I'm going to Control C and put a Control V there. And then I have to change this formula, I think. It's I7, I7, I7. So let's make sure these are right. So that's going to the wrong place, and we now need to change this one to I. And now we're going to copy this down. And and we have to find our mean here. Is that what this is? Yeah, that's the average of the mean. So it's going to, we got to sum all this up. So let's sum all this up. Boom, boom, boom. Sum all that up. All right, so when we sum all these days up, right, the total is like how many days in total. So here, right, we sum up to get our total. And then when we get our total, we divide by how many data figures there were, and we get our mean. And then our range on that, so our range here, the range here is difference between the biggest and the smallest data set. So the difference between the biggest and the smallest data set is we have an 1892 minus a 1435. So our range there is 457. And then the difference here, I'm just checking to make sure this is calculating right. I2 minus I9, that's good. But I'm going to copy this down here to make sure that's right. Control C, Control V. So those, and I can look at those here, right? Those are what I want. I2 minus I9 right there. And then this one is going to be to square each of those. So those are correct. And once each of those are squared, to calculate my variance, I'm going to add them up. So I'm going to add up all those squares, because our formula here says you find the difference, you square it, then you add them up, and then you divide by n minus 1. So I found the difference right here. So the difference between 1,500 minus the mean is 150.4. 1,750 minus the mean is 99.6. And then I square each of these, and I get these, and I add up each of those squares, and I get that. And then I divide by n minus 1 here, or 4, and I get this. And then I take the square root of that, and I get 185. Well, this is kind of hard to compare 2 to 11.6 to 185, because these are at different scales. Like for normal screws, nuts, and bolts, we could go to John or Robert, and these are the kind of days it takes to get our stuff once we've placed an order. But over here, we're really talking about years. These were on the scale of days, and these were really, there were so many days, we really start thinking about them in terms of years when we order a rocket. And so we need some way to sort of normalize standard deviation between like data sets where they have different scales, like just a few days or many days. How do we normalize that? And so to do that, we have a new measure, and that new measure is coefficient of variation. And to normalize it, we take the standard deviation and we divide by the mean, and then we multiply it by 100. Okay? And so this will tell us, it normalizes it, if we take our standard deviation and we divide by the mean, or we take our standard deviation, divide by the mean, we take our standard deviation, divide by the mean, it tells us how many means, or what fraction of a mean, is in the standard deviation. So it normalizes it between data sets with large scale. Let's see that in action. So I'm going to right click this, do a row below, and this one is called coefficient of variation. Coefficient of variation, and that's abbreviated as CV. CV. And the abbreviation CV also stands for, in a separate context, curriculum vitae. I don't know if I'm saying that right. And a curriculum vitae is what a resume is called in academia. Kind of interesting. So coefficient of variation is going to be equal to, I take my standard deviation and I'm going to divide my standard deviation by my average or my mean, and then I'm going to multiply it by 100. And if you're confused about the order of operations, you could do it like this. You could put parentheses around that, and it's going to take your standard deviation, D12. It's going to divide it by your average or your mean, B9, and it's going to multiply it by 100. And when you do that, you're going to get 20%. But in a spreadsheet, if I come up here and I click percent on that, it's going to give me 2,000%. And so what I need to do in a spreadsheet, when you click percent, it multiplies it by 100 for you. So I'm going to take that 100 out of there. And you can see that up here. I'm working in the small formula up there. And I'm going to press enter, and now that gives me 20%. And if I come over here and I do the same thing, it's going to be my standard deviation. My standard deviation divided by my mean, and this is and it gives me, it already kind of figured out that should be a percentage, gives me 116%. And if I do the same thing here and take that and divide it by my mean, it's going to give me 11.25%. And so the coefficient of variation allows us to look at the variation on a scale that's normalized by the mean of the data set that we're working with. So the standard deviation is 20%, 2 over 10 of the mean. The standard deviation is 115% of the mean, right? So 11.59 divided by 10 is 115%. The standard deviation, 185 divided by 1650, is 11% of the mean. So this actually has like the least variance, which is interesting. This has the next least variance, and like on this scale, it's hard for me to kind of see what is the variance. Those numbers just look big. On this scale, I could wrap my head around 2 days. I could say, oh, 2 days either side. That makes sense to me, right? So it's 2 days either side of the mean, 20% of the mean. This one's 11% of the mean, so it actually has less variance over here, but that's what the coefficient of variation does. So we have variance. These are numeric measures to provide descriptive statistics of our data set. We have variance, we have standard deviation, and then we have the coefficient of variation. And this is telling us what is the dispersion, what is the variability. These four measures, range, variance, standard deviation, coefficient of variation, are telling us like what is the dispersion, what is the variance of our data around the mean, right? Because we not only want to know the average, how long does it take on average to get something, but what is the dispersion, right, around that average. So each supplier took 10 days, but this person has a range of 4, this person has a range of 28. They have a variance of 4 and 135, or a standard deviation of 2 and 11, and a coefficient of variation of 20% or 116%. Having this data, we could really start to make more informed decisions about who we're going to go with as our supplier, and whether or not their dispersion, their variance, their variability around the mean is like completely out of whack, or if it's like, when it's normalized in relationship to the mean, if it's like, like acceptable. Like, the fact that, the range here is 457 days, and there's 185 days of standard deviation. The standard deviation of a data point around the mean is 185 days. That might seem like, oh my gosh, that's a lot of days. But in relationship to the longer time it takes to have something supplied, it really isn't that much. It's only 11% in relationship to the mean. And so the coefficient of variation tells us that, hey, you know what? That's actually pretty acceptable in terms of dispersion or variability, considering how long it takes to build a rocket. So that's like thinking about what is the measure of central tendency, like the average, and then also what are measures of dispersion or variability, like range, variance, standard deviation, coefficient of variation, and hopefully that gives you some really great insight into how these different measures work. All right, I have to go to class. I hope you have a great day. We're all, doing what we can to get through this, so keep working. Do the work when you can do the work. Learn some amazing things. These amazing things are going to empower you to do better in whatever career you go into, and it's going to give you a solid understanding of using numbers and working with numbers and understanding numbers so that you can make better decisions in everything you do in your life. See you next time.